Very happy to introduce Chris Donahue, who's an assistant professor at CMU, and in his spare time he helps Google DeepMind with the Magenta project on generative music AI.
Cool. Yeah, thank you for the introduction. I'm really excited to be back at SANE and to have this opportunity to talk about the expanding horizons of generative music AI research. So to start off, I wanted to kind of take a very broad look at the kind of status quo in the music industry, especially on the commercial side of things, in terms of the kind of main relationships between different stakeholders in the music industry. And these relationships have been fairly stable for the past 10 to 15 years, sort of since the advent of the streaming era of music. Where basically how this looked is that we had consumers, non-musicians, listeners, listening to music through distribution platforms like streaming services and social networks. These distribution platforms, of course, populated by music created by musicians, sort of closely intermediated by record labels. And we had these regulatory agencies and pro-organizations like the RIAA and ASCAP that sort of kind of keep this ship turning and kind of ensure that compensation is flowing between various stakeholders. And kind of for the past 10 years, there's also been this sort of like disconnected subgraph of researchers working on music generation, or something maybe we're now calling generative music AI. But for a very long time, this work was really sort of isolated and not really having too much of an effect on the actual sort of commercial side of the music industry. But pretty much overnight, that has really kind of dramatically changed. And in particular, one thing that's maybe front of mind for many of us is this recent emergence of startup companies like Suno, our local Suno, and Udio, which now allow non-musicians to be able to generate sort of full songs on topics and styles of their choosing, which was sort of a capability previously only held by musicians to be able to do this type of thing. So we've probably all heard lots of this stuff recently, but as kind of a grounding example, I can now take a prompt like a Celtic punk song about a research conference called SANE, held in Cambridge, MA, and pump it into Suno and get something like this. Be a good transition to the drinks after. So raise your toast to the vines that lay in the halls of Wales, it was fun to make. The conference of speeches down in the heart of Cambridge, knowledge profound. Yeah, pretty impressive. It's actually been stuck in my head for a couple of days since I made these slides. So for many of us that have been working in this space for some time now, this is a pretty staggering sort of development. Like, it kind of emerged basically overnight. Like, the systems went from not really working that well at all to suddenly kind of really generating music that is listenable and that maybe even starts to compete with actual musicians. And indeed, that's actually something we're already seeing happening. So there was this case of a user who was uploading music to these streaming services that was generated by generative music AI. So it's now the case that musicians and by proxy record labels are sort of competing with generation for listener attention. Musicians have also been sort of more directly reconciling with this technology. This was just alluded to in the last talk during the QA. Of now we have the ability to also sort of do deepfake or voice cloning of famous artists, and there's famous examples of tracks that have been uploaded to social media that were sort of deceiving the public into thinking there was some new Drake or The Weeknd track, featuring these musical superstars. So obviously lots and lots of ethical issues, moral rights, right of publicity infringement. But also, potentially there's been some other headlines that suggest that these types of technologies could even offer new revenue models for artists. Musicians like Grimes and Charlie Puth actually licensing their voice so that others can use them to sort of incorporate their voice into their own tracks. So kind of both sides of the equation here. And record labels, obviously, kind of on full alert, forging sort of new licensing agreements and data models with different tech companies to try to get ahead of this. And the regulatory agencies are also sort of scrambling to catch up, starting to sue some of these music generation companies. And this is not specific to music. This is kind of happening across generative AI in general. So, OK, so lots of headlines here. What's the point? I mean, the point is that I don't think it's hyperbolic to say that in the past 1 to 2 years, this technology is really starting to fundamentally reorganize the music industry in a way that really hasn't happened since the advent of the kind of music streaming era. However, I would argue that the research that we're sort of working on as a research community in this landscape still remains somewhat more narrowly focused on sort of the core underlying machine learning or generation technology, as opposed to kind of looking more broadly at the changes that have happened across this very important and impactful social landscape. So, one question is why should the scope of music AI research expand in response to this kind of changing landscape, or why should it? And one of the reasons I think that it should expand is because there are really profound opportunities and risks here. So, on the one hand, I think there's the opportunity for music to potentially really flourish under this new technology. Music creativity more accessible than ever. Non-musicians can create music. There's sort of expanded creative potential even for artists, potentially. Music can become more personalized or contextualized. So there's lots and lots of really exciting opportunities and sort of carrying on a long tradition of technology driving music forward. But in this case, I think there's some real potential for sort of profound risks to music. Music is already really heavily commodified through streaming, and now this generation stuff kind of just makes it infinitely abundant. There's eroding incentives. Maybe we don't there's less and less motivation to pursue traditional forms of music education if we can just generate stuff now. And there's, of course, lots and lots of potential for harms to different musicians, creators, and musical cultures. And so I think it's important as a research community that we sort of recognize the gravity of the situation and sort of what we're playing with here, and ask ourselves, sort of what can we do to pursue more of this sort of opportunities that could come from this technology while also navigating these fairly profound risks. And I've been thinking about this question a lot, specifically because it's kind of coincided with my formation of a new research lab and kind of being forced to reconcile with this question of whether or not the work I and my students do is going to look anything like the kind of work I did as a PhD student and a postdoc. And I don't pretend to have all the answers here. These are still very early days of this kind of technology making its way into the real world. But one of the long-term goals I really want to work towards, that I've sort of settled on working towards in our lab, is pursuing a more kind of holistic view of generative music AI research that is kind of encompassing of this broader landscape that is kind of now emerging. I'll share some thoughts about that at the end. In the short term, we've been working really specifically on a kind of more narrow goal, which is supporting more iterative forms of musical creativity that kind of incorporate music more as a process rather than sort of something to kind of automate the resultant product. So that's going to be kind of the main focus of this talk, and then I'll kind of zoom out at the end to kind of share more of this vision of holistic research in this space. So to kind of, I think it's to talk about sort of this more iterative kind of view of supporting musical creativity. I think it's important to establish that music is kind of both a process as well as a product. So on the one hand, a goal of creating music is often to create a compelling product, so to speak, to create a nice recording or a live performance or something that you can share with others. But music is also very fundamentally a process of creativity and discovery, and that process is has intrinsic value as well. It's not just the product. The process is something that we as humans have always wanted to pursue, and I'd argue will continue to want to pursue, even in a landscape where we can sort of take a shortcut and just generate the resultant product. So I think generative AI specifically has a lot of tremendous potential to both, on the one hand, it might sort of, you might take a look at something like Suno or Udio and think, okay, we've kind of solved music, right? We've automated this product, we can generate music now. But I think this is a bit of a narrow view. Music is so much more than just what you hear through the streaming service. It's this like fundamentally social and creative activity. And I think there's similar potential for generative AI to really enrich the process. And that's kind of what I want to focus on today. So as a kind of grounding example, I think that supporting music creativity as a process requires supporting a couple of key sort of characteristics that existing sort of state-of-the-art generative models don't really support very well, in particular precision and iteration. And so as an example, there's this famous example of Modest Mussorgsky, a composer who was very inspired by a painting of the Great Gate of Kiev, and kind of from that inspiration wrote a suite of pieces called Pictures at an Exhibition. And what I'm trying to convey with this example is that the sort of core artistry of music, like musical creativity, has always been about this goal of trying to convey really high-level concepts and emotions through sort of very precise manipulation of much lower-level concepts like notes and rhythms and things like that. And that is part of the artistry of music. That is why it's an interesting art form. It's this really artisan kind of manipulation of these precise kind of concepts. And it's not something that can be done sort of, especially in terms of like music composition, it's not something that can be done sort of in one pass. It's this iterative process where maybe we start by coming up with a melody idea, and then we harmonize that melody, and then create variations on it, and sort of kind of wander around in this hierarchical fashion until we arrive at the final sort of output. So it's this really iterative process. And I would argue that the current sort of modality by which we interact with state-of-the-art generation models does not really well support this process. So for example, I could pass a text input like a grandiose piano arrangement evoking the majesty of the Great Gate of Kiev into Suno. On the one hand, that's kind of cool in that, like, if the art form of music was always about conveying high-level concepts, then we've kind of maybe we've taken a shortcut here, and now we can just type a text prompt. But personally, I feel that like it's really still important to the process to be able to kind of manipulate things at a much lower level. And so this text input only gives us very sort of imprecise global control. And finally, the fact that these systems output sort of mixed audio waveforms is kind of fundamentally inhibits iteration, because as we all know, we all work in audio. It's very hard to take a waveform and manipulate the audio samples as a way of editing. We want to edit at a higher level. We want to change text representations if we're talking about speech, or we want to change notes if we're talking about music. So it's a kind of one. It stands to reason that to better support this process, if we could improve the precision and also have systems that allow us to iterate better, we might be able to do that. OK, so in today's talk, I'll talk about a couple of our recent projects on attempting to improve the precision of control for music audio generation, as well as some of our work on iterative workflows, which are more grounded in symbolic music. So to start out, I wanted to share about a recent project called SingSong, which I worked on with a very large team at Google DeepMind. And the basic premise of SingSong was that we wanted to generate accompaniments for singing voice, allowing someone to essentially kind of control a music generation model using their own voice. And this kind of allows users to have very precise control over the overall timing and sort of melodic kind of development of the output music. So for example, as a user, I could, well, not me, but someone else could sing something that sounds like this.
When it's all over, when we are made.
You could pass that vocal performance into SingSong, which will generate an accompaniment that sounds like this.
When it's all over, when we are made. Oh, how do I know that?
SingSong also, that's a particularly professional sounding recording. SingSong also works well for amateur recordings like this.
Et ça fait aller les bleus. Et ça.
Sound example? Anyone?
Et ça.
OK, maybe. Yeah, OK. Well, maybe we'll come back to that if there's time at the end. Oh, Google Slides. Love-hate relationship. All right. Well, OK, so jumping into a little bit of how this actually works, at a very high level, We have a couple different phases here. We have a training phase, and in the training phase, we basically manufacture a lot of supervised data for this task by taking a large music audio data set consisting of audio mixtures, using source separation to split those into corresponding vocals and instrumental, and training a model to attempt to reconstruct the instrumentals given the vocals. At inference time, we can take the vocals, pass them into SingSong to generate a new instrumental, and simply mix the resultant output with the vocals to produce the final output of the system. Now, that's a very high-level overview. I want to go a little bit deeper into the weeds of like how this SingSong magic box actually works. So we base our method, our method is strongly based around AudioLM, which is also a research project that came out of Google a couple of years ago, which is a hierarchical approach for modeling or for doing audio generation. And the basic way it works is that we start with waveforms, so continuous audio waveforms. And we send these waveforms through a pair of kind of parallel tokenizers, respectively referred to as the semantic and acoustic tokenizer. The semantic tokenizer is a self-supervised model trained in sort of a BERT style or masked language model fashion. It produces a very slow stream of tokens, which conceptually are sort of higher level tokens. They encode like higher level details about the music. And we also have a codec, a discrete codec model, which you've heard about at several other talks today already. So basically, this model will take the audio and encode it into a much higher bandwidth set of tokens relative to the semantic tokens, at least. And then these tokens actually capture very fine-grained details about the audio. You can actually fairly precisely reconstruct the original audio from just these tokens. But they're very long. These are incredibly long sequences. There's roughly 600 tokens per second in the codec that we use. So we adopt a hierarchical approach to be able to model these efficiently. And so we model a joint distribution of the semantic tokens and the acoustic tokens. In the first stage, we simply model just a sort of long sequence of the semantic tokens. This kind of allows the model to conceptually generate an initial plan for how the output audio will kind of proceed at a high level. And then we generate the coarser acoustic tokens given the generated semantic tokens. And finally, we generate the fine-grained acoustic tokens given the coarse tokens. This is kind of similar to the delay pattern that Jiao was just describing, although this is kind of like using linearization and hierarchy as a way of overcoming the same problem of modeling these very long sequences. So, but AudioLM is just a way of modeling single streams of audio, and in this case, we have this sort of multi-stream setup. So how do we extend AudioLM for audio-to-audio accompaniment? That's what we propose to do in this paper. So basically, we take mixed music waveforms, and like I mentioned, we use source separation to split them into vocals and instrumental. And then we encode the vocals and instrumental independently using a semantic tokenizer. And we also encode the instrumental specifically using the codec model. And then our generative modeling, or hierarchical approach looks fairly analogous. We start with a model that converts the vocal semantic tokens, or generates instrumental semantic tokens given vocal ones, and then a model that generates coarse acoustic tokens given both sets of semantic tokens, and finally a method that simply kind of produces the fine-grained instrumental tokens given the coarse-grained tokens. So it's a fairly straightforward adaptation of AudioLM. There's a couple of tricks that we needed to do to get this to work. One of the interesting things is that if you just naively use source separation, then the model essentially tries to learn to reconstruct the original instrumental from the artifacts that are hidden in the vocals. So we had to do some clever things to actually kind of get this thing to generalize to vocals that weren't source separated. But this is a fairly basic setup that would maybe work well for a lot of other audio-to-audio kind of generative tasks. OK, so that's kind of how the method works. There's a couple drawbacks I want to highlight, especially to motivate some other work we've been doing recently in this space. One of the drawbacks is that we require very large volumes of training data to be able to train this model. We use roughly 1 million songs, or 46,000 hours. Also, as you may have noticed, we only have this kind of vocal control here. We don't have text control. And as you can imagine, it might be really useful to users to be able to control sort of the style of the output instrumental using text. OK, so with all that in mind, I wanted to share a little bit about a recent project led by a former student, Shilun, who's now here at MIT, called Music ControlNet. And the basic goal of Music ControlNet was to sort of complement this type of text control that we're now increasingly familiar with also more precise forms of control. So using our model, for example, you can pass in a global text prompt like happy and jazz, as well as a more precise prompt representing a melody that you want to hear in the output music as a user. So that might sound like this. Hopefully I have sound examples. I don't think so. I think it's buffering. Any sound examples? Can't load this audio right now.
Is it online?
Mm-hmm. Cool. So there's your melody control. And then with the global text prompt, Music ControlNet will output this. Come on. Come on. There you go. Cool. And you can see, as you can maybe see from the spectrogram, there's actually really precise correspondence between the input control melody, which we are sort of visualizing here, as well as the output. We can also have, this works for many other types of precise control, such as rhythm. So we can pass in a rhythm prompt like this, generate this. We also looked at specific control for dynamics. So we can sort of input a kind of overall volume curve that we would like to hear in the resultant audio. Cool. Moreover, these controls are also composable. So we can pass in multiple of them, such as a melody and the dynamics, and get this output. Cool. So hopefully you can kind of see and hear the correspondence between these things. So how do we actually do this? Kind of a basic sort of three-step process here. We first extract these control signals directly from the music audio data set that we have. So we do a basic sort of chromogram processing to extract a melody. So we have this kind of the 12 pitch classes and the energy in each of them across time as one control signal. We use a pre-trained beat and downbeat prediction model called MadMom to extract a proxy feature for rhythm. And then we also use good old-fashioned signal processing to kind of extract RMS amplitude from the audio waveforms, which we interpret as sort of overall indicative of volume or dynamics. And then we take these control signals and we use them to adapt a pre-trained spectrogram diffusion model. So we have this pre-trained text to music model, which has been trained to generate these spectrograms given text. And we train these lightweight adapter branches that consist of taking the control signal, embedding them with an MLP into these sort of time-varying representations, and then using zero convolution or identity layers to kind of initialize a way of injecting that time-varying representation into an original copy of the layer weights. And we can sort of train all these branch parameters in an adaptation phase. This turns out to be a really efficient, both in terms of like a compute and parameters way of adapting a model with these kind of new, more precise forms of control. And this was heavily inspired or adapted from work in the image domain on ControlNet. Finally, to evaluate this thing, we can sort of measure overall retention of the controls. So we can take the input control, use them to generate a model output, and then re-extract the original control signals from that model output, or use the control extraction algorithms to get them from the model output, and then simply compare the two to see how well the controls have been preserved from the input to the output. And this turns out to be a kind of great general setup for kind of evaluating control correspondence. So as Greta mentioned, computer science requires LaTeX tables in your slides. So here's mine. So basically, we feed, in the first set of experiments, we feed in individual control signals into the model, so just feeding them in one at a time, and measure the correspondence. And we see that Music ControlNet does indeed sort of give us these more precise controls when you feed them in one at a time, meaning the correspondence values are much higher than when you don't feed in the controls. And moreover, we see that these controls are composable when we feed in multiple of them at a time. The correspondence or retention evaluation does not degrade relative to the sort of single input case. And that's also the case not only for the precise controls, but also for the text control. So we kind of conclude that these controls are both precise and composable. Moreover, Music ControlNet is very data and parameter efficient. So compared to Music Gen Melody, another paper that also has this kind of similar type of, has an identical type of melody control, we use an order of magnitude less training data and 37 times fewer parameters. But in spite of that, we get 14% better melody control retention, as well as better generalization from the sort of in-distribution controls that we encounter that were extracted from audio during training to the ones that we might anticipate users passing in that kind of look a lot cleaner than the ones we extract. And also we can sort of look at a bird's eye view of comparing this to SingSong. It's very apples to oranges, different modeling architectures, different kind of control tasks, but still our model is significantly more data and parameter efficient. So there's a lot of potential for this method to be able to be used efficiently to kind of incorporate these more precise forms of controls into music generation models. Okay, so kind of zooming out, one interesting observation is that both SingSong and Music ControlNet rely on a very similar protocol of taking data sets of music audio waveforms and extracting control features from them. So in SingSong, we extract the vocal performance, and Music ControlNet, we extract the melody and the rhythm, et cetera. And so, looking at this, one kind of observation is that if we really care about improving the precision and incorporating new and better forms of control into these music generation models, it's maybe potentially more important that we focus on improving music information retrieval as opposed to kind of improving the core generative modeling methods themselves. I think at this point, we have methods that, given sufficient amounts of sort of X to Y kind of data, we're going to be able to learn that transformation of X to Y. And so there's kind of this renewed importance of kind of classical music information retrieval in terms of manufacturing that type of paired data for training these controllable generation models. And then kind of back onto the kind of general theme of supporting more sort of process-oriented forms of musical creativity. Our work really improves the precision in terms of our ability to input precise kind of control to these models. But the fact that we're still doing kind of mixed audio waveform outputs kind of fundamentally discourages iteration because, again, it's very hard to manipulate these audio waveforms. So I wanted to jump over now to talk about some of our recent work on supporting kind of more iterative forms of creativity that center around symbolic music. And hopefully you'll forgive that this is about symbolic, even though this is an audio workshop, but I think it'll be of some interest to this audience. So part of the motivation for this work comes from trends we're seeing outside of music. So for instance, in the programming domain, we have this really interesting ecosystem where programmers write code, which is used to train generative AI models, which are then incorporated into generative AI assistant tools like GitHub Copilot, which programmers in turn use to write more code. This sort of ecosystem that has emerged in the programming landscape is really inspiring to me. It's kind of been this best of both worlds broadly beneficial thing where not only do programmers feel more satisfied, or sorry, not only are programmers more productive, like measurably when they use these tools, they also find the work more satisfying. And I think it's a really compelling premise to ask whether or not those same sorts of benefits can be obtained for creative workers or for musicians as well. But unfortunately, a similar ecosystem doesn't really exist for music. So musicians write music, which is used to train these generative AI models, but we don't have this analogous sort of ecosystem of assistive tools that actually gives those tools back to the original data creators to allow them to do newer and exciting things creatively. And understandably, this has led to quite a lot of skepticism among musicians about these tools, especially when you compare, like, very in a hand-wavy sense to programmers who are arguably potentially very excited about some of these tools. So with this work, in a recent project, we built a system called Hookpad Aria, which is intended to intended to be sort of a glimpse at Copilot-like co-creation tools for musicians. And in particular, we focus on a group of musicians, pop songwriters, who use an online website, Hook Theory, to compose lead sheets, where lead sheets are this kind of like the essence of a piece of Western pop music consisting of the melody and harmony. So I'll play a brief demo video of Aria, and mainly because I'm worried about my internet to show the real demo. But I would encourage you, the demo is live, so you can check it out too if you're interested.
Here's a quick demo of Aria. This is the Hookpad interface, a basic sketchpad for writing pop lead sheets. I currently have it set to D minor at 142 beats per minute. Let's say I have an idea for a basic melody that sounds something like this. However, I'm having trouble thinking up a harmony to go with it. Let's use Aria to suggest some initial chords to go with this melody. To do this, we can simply select the region of measures we want to generate for, click on the Aria button, and press Create Chords. Aria will begin generating multiple suggestions for us to try out. I like that first suggestion okay, but let's try one more. Okay, great. I like where this is going. I have some ideas of where the chords could go from here, so let's quickly punch those in and see if Aria can help us create a new melody to go with them.
Okay, yeah, not bad. But for those of you who are familiar, especially for those of you who are familiar with using tools like digital audio workstations and using tools like GitHub Copilot in a programming context, this workflow probably looks fairly familiar. We are kind of working in the conventional workflow that we're familiar with in our digital audio workstation, but now we have access to this assistive tool that can sort of help us get unstuck. So one of the big challenges in building Aria is that musicians compose music in this very non-sequential fashion. So here's a time lapse of someone using this piece of software, Hookpad. And as you may notice, as they compose music in this software, they're kind of always sort of jumping around and backtracking and rewriting earlier parts. They're not just writing sort of music in a left to right fashion. Especially when we're talking about discrete data and modeling discrete data, one of the most sort of powerful generative modeling architectures or sort of methodologies we have is language modeling, but language models sort of by default don't support this type of sort of non-sequential generation. So how do we incorporate these capabilities into language models? And I'll start talking a little bit about language now because some of the methodology we developed to support these capabilities was originally invented within the context of language generation. So basically, again, the key tension here is that language models typically operate sequentially. Given the past, they predict the next word. But in a co-creation context, creators may want kind of more fill-in-the-middle capabilities. They may have some notion of both what happened in the past as well as what might happen in the future, and they want to sort of predict the middle and kind of fill in the blank. And so, sort of what this kind of task looks like at a high level is that we have, in language, is that we have a document that might look like the scientist was blank by the results, and we want to output a completed document that has a reasonable words to go in that blank. And so we're sort of trying to model this distribution over completed documents given incomplete ones. And an interesting thing to point out is that this sort of the ordinary language modeling case is actually sort of you can view as a special case of fill-in-the-middle generation where the blank happens to occur at the very end of the document. So back in 2020, we proposed a very simple method to sort of imbue language models with this type of fill-in-the-middle generation capability. So how does it work? We start with training data consisting of complete documents. We sort of randomly mask those examples to kind of create artificial fill-in-the-middle examples. So we mask out the word shocked, and we also keep track of what originally went in the blank. And then we simply create these kind of fill-in-the-middle training examples by concatenating the corrupted or masked document with the original answer that went in the blank. And this is just basically a really simple rearranging of the order of the sequence, but it kind of unlocks this powerful capability to be able to just train an ordinary left-to-right language model on these types of fill-in-the-middle examples. And then by the time the model actually wants to generate the word shocked, it actually has the past and the future context in its history. So at inference time, it's pretty straightforward. We take as input an incomplete document. We generate an answer using our trained fill-in-the-middle model. And then we simply stitch that answer into the original document to produce the final output. OK, so we take the same, we take a GPT-2, well, this is back in 2020. So we took a GPT-2 model, and we fine-tuned it on 3 different data domains, both using kind of ordinary language modeling, as well as our proposed fill-in-the-middle fine-tuning paradigm. And we evaluated all 6 of those checkpoints on their corresponding fill-in-the-middle task. And we see, as expected, our proposed model does actually learn to fill in the middle, meaning it is able to sort of lower its perplexity when faced with future context. But interestingly, we also observe that when we evaluate the same 6 checkpoints on ordinary language modeling, we see that the performance is actually completely steady, or fairly steady across these. And so again, because sort of ordinary language modeling is this special case of fill in the middle. So what we conclude is that we're able to sort of imbue language models with these capabilities without actually sacrificing their sort of their original sort of data generation ordering. OK, so that was within the context of language. Back talking about music. So fill in the middle is a helpful controllable generation task in the context of music. We might have some multi-instrumental music that looks like this symbolically, and we want to sort of fill in the middle in blue. So that can be very helpful. But music has this additional interesting property that we don't find in language, where there are sort of these interleaved streams of notes that are sort of codependent on one another and occur at the same points in time. So how can we extend this method to support tasks like accompaniment, where we want to, say, generate an accompaniment to go with sort of an input violin melody or something like that? So with that kind of general premise in mind, a group of collaborators at Stanford recently set out to build, to try to sort of generalize this fill-in-the-middle approach to be able to support any sort of rich co-creation kind of generation capability or ordering that we want for music. And the basic way it works is that, just like in the fill-in-the-middle for text example, we start with training data consisting of sort of just uncorrupted, MIDI music that we can find on the internet. And we go through each note in the MIDI and partition it into two disjoint groups. One, a group of what we call controls or inputs to the model, and one that we call events. And we can create many of these different types of partitions to support these different types of co-creation tasks that we want to support. So for example, for fill in the middle, the inputs are the left and the right, and we're trying to generate the middle. In the accompaniment case, the inputs are, say, this violin melody, and we want to generate the piano. OK, so now we have these 2 streams of kind of partition notes, and we're trying to train a generation model that can generate the events given the controls. And we want to use ordinary language models to do this because that's what we know how to scale, and it's great to map onto the space of existing methods. So you can so how we actually do this, you can visualize these things as kind of 2 streams occurring, two streams of events occurring on a common timeline. So we have a stream of controls, and we have a stream of events. The controls, again, are the inputs. And one option but we have these language models that can sort of only reason about these sort of sequential 1D streams. And so how do we map this kind of richer structure onto an LM training examples? Well, one thing we can do is just sort of naively interleave. But the downside is that we don't have any context of controls that are coming in the future when we're generating the present. So this isn't going to really support the types of infilling operations that we're aiming to support. Another thing we can do is we can take a cue from our work on language and adopt this kind of sequence-to-sequence style approach, where we take all of the controls and we simply prepend them in the sequence, and then concatenate all of the events, and then we can just train our favorite LM or sequence-to-sequence model to try to generate the events given the controls. Now, in practice, this sounds like a really good idea in theory, but in practice, language models have these kind of finite context windows. And one issue here is that if we do this, the relevant controls, meaning the ones that are close by in time to the events, might actually be evicted from context by the time we generate. So in this case, if you look at event ej plus 2, it is actually its closest control is the first one, UK, and that actually won't be in this finite context window when we're generating ej plus 2. So what we propose to do instead is kind of somewhere in the middle of these two. So what we do is we take the controls and we artificially shift them forward in time by some hyperparameter delta. And then we interleave in time order. And what this does is this allows the model to sort of anticipate controls that are coming up to delta seconds in the future. So for example, when we're generating event EJ, we now have context of UK, which originally was actually something that was after EJ. So this is great. This gives us some it's sort of a trade-off. It gives us some amount of finite future context, but it also allows us to co-locate the targets, or sorry, the events I should have written, near their relevant controls. And this is potentially something that has broader applications, to audio in general. In particular, lots of tasks in audio processing have this kind of same structure where we have two different streams of data and we're trying to translate between them, such as ASR or TTS. You can imagine. You can think of this as sort of a localized sequence-to-sequence, right? Where we're, by default, sequence-to-sequence is anticipation with a hyperparameter delta of infinity, where we're shifting everything before, we're shifting all the inputs before we do any outputs. So it's potentially a really powerful paradigm that works outside of the domain of symbolic music. Okay, so to kind of summarize, we use this method to train lots and lots of different controllable capabilities for this Aria project that we were able to sort of integrate into this Copilot setup. Zooming out, one of the reasons I'm really excited about things like this is that Aria is now giving us this really interesting data flywheel to better understand the kind of nature of human AI music co-creation. We have this model Aria, which is, since we launched a few months ago, has now provided over 300,000 suggestions to musicians, to 3,000 unique musician users who have now provided lots and lots of feedback. And there's a lot of really rich opportunity to explore how we can better align these models with human preferences, personalize them to individual users, or even explore sort of evaluation in the wild through things like A/B testing different model candidates. And completely outside of the context of audio and music, but sort of relevant to this theme of in the wild evaluation, we also recently launched a system called Copilot Aria just this week, which is also trying to look at this question of can we actually evaluate models in the wild in ways they're actually being used. So Copilot Aria is a VS Code extension that you can download that will, as you code, it will generate suggestions from multiple different language modeling backbones, and users can sort of decide which of those suggestions is more appropriate for their context. And so the reason I'm excited about this project as well as Aria is that it's really kind of acknowledging that these models are increasingly being used in the wild in real use cases and asking whether or not we can actually evaluate them in those contexts rather than sort of statically in offline settings. Okay, so finally, to sort of zoom all the way out, I think this theme of in the wild evaluation connects to this kind of broader vision of having a more holistic view on this research landscape. And so to kind of reiterate, I think it's important that we acknowledge as a research community that the landscape of this technology has become extraordinarily complex, and ask ourselves sort of what can we do as a community to respond and kind of guide this technology towards better outcomes. And I think one of the obvious things we can do as a community is try to collaborate with more diverse stakeholders. So not only the kind of music industry stakeholders I've been highlighting throughout the talk, but also lots of other stakeholders like musicologists, cultural organizations, legal scholars, music educators, who are increasingly having really impactful input into this increasingly complex landscape. And I think collaborating with broader stakeholders is a great way we can sort of pursue this more holistic research vision in music generation or generative music AI. Where there's still going to be lots and lots of research on sort of the core machine learning technology that's driving this sort of movement forward, the data sets, the methods, et cetera. But there's also a level of research beyond that in terms of acknowledging that people are increasingly interacting with these systems and asking questions about how we can about the nature of that interaction. And as I look across the landscape, I kind of see arguably in a very hand-wavy sense, the center of mass of research is maybe here, where we have lots and lots of research on the core machine learning technology and some research on on sort of more of the HCI side of things as well. But there's this whole enormous landscape of new sort of broader societal questions that are emerging here. We even we were alluding to some of them in the last presentation about AI content detection and watermarking, these technical research problems that can really help us navigate this very nebulous economic and policy landscape that is emerging from this technology. And moreover, there's obviously music is not just an economic commodity, it also has significant cultural and societal value. And there's lots and lots of really broad research questions that we need to start looking at to understand how this technology is really going to impact us as a society. And this is an ongoing process. I'm not arguing that I'm currently doing all of this. I would love to, and that's kind of the long-term goal of the lab. And in this talk, I've looked at a very narrow set of things that are on this slide. But I'm really excited about sort of moving us as a community in having all of us sort of rally and move in the direction of looking at this space more holistically. And with that, I'll say thanks and take any questions.
So maybe time for just a couple quick ones.
Hey, Kyle.
Hi. In the spirit of moving immediately away from this slide and asking a technical question.
Sure, yeah.
In
fine.
the music ControlNet example, you kind of have, when people give inputs, they're kind of very clean, and the outputs from the system itself are kind of messed up, and that's going to be closer to what the DSP tools originally trained the model with.
Yeah.
If you just run this inference forward on its own outputs multiple times, what happens?
Sheelan, have you tried this? Have you recursed?
No, I haven't tried this before. But
We should try it.
Okay.
Do you still have access to Adobe? Okay, yeah, that's a really good idea, though. What do you think would happen? Is it just gonna
It would either blow up or stabilize, right?
Okay,
It's one or the other. And that leads to my natural next question is learning to map from the human given controls to what DSP tools give you and vice versa. But
Yeah, that's a really good question. A very broad sort of generalization problem. A common theme actually across both SingSong and Music ControlNet. We had to work really, really hard with the SingSong project, like I was kind of briefly alluding to allow it to generalize to isolated vocals as opposed to vocals with sort of source separation artifacts. The first time I pumped isolated vocals into the system after hearing the mind-blowing results it was giving me for sort of in-domain control inputs, I was so discouraged because I thought we had cracked it, and then all of a sudden I realized I was just it turns out you can actually really precisely reconstruct the original sources that you separate from artifacts. Maybe that's of interest to other people in the room. But yeah, so broad answer, I don't know that we have a great answer. Really challenging generalization problem. I think we need to be looking across the space of research and generalization and ML to crack that one. And we saw empirically that in our work, our model did generalize well to out of distribution controls, and so there's maybe an argument and that inductive bias plays a strong role here. But it's a good question. I don't have a great answer yet.
Thank you.
I think I have a question regarding the metrics. I think you try to use professional music composers to check how well you're doing. I believe a few years ago I did something similar in 2018 I had working with a professional music composer. He said, you want to check how creative the music composed is and how interesting the song is. Do you think there is something the community can do in terms of the evaluation, especially the automatic evaluation? Because you can see for the TTS, more and more automatically evaluation methods are there.
Yeah, it's a really great question. Yeah, in general, I think evaluation is one of the most challenging and also one of the most exciting, research problems regarding working in like this more creative space because it is really difficult. I've been thinking about a lot about evaluation recently. We have some ongoing work that I'm sort of not quite ready to share just yet, but so one more concrete answer, one slightly more vague answer. A more concrete answer is I'm really, really excited about this trend towards sort of in the wild evaluation, about thinking about how we can collect listener feedback from real users in a scalable fashion. And so things like Chatbot Arena, for instance, are really inspiring there. Like we have a service now where people are sort of their own volition going to this website and giving their feedback between two different models. And I think I'm really excited about kind of trying to build similar scalable evaluation tools for audio, music and audio sort of evaluation. On the automatic evaluation side of things, maybe stay tuned. I think we've made a lot of progress in some recent work we've been doing on automatic evaluation, but we're not quite ready to share it yet. I wish I, yeah. Maybe we'll keep that under wraps for just now, but we can talk offline potentially.
Looking forward to it.
Yeah.
I'm interested in knowing about the clever technique you use to remove the artifact from source separation.
Oh, yeah, maybe I oversold it by calling it clever. We add noise to the vocals. So if you add sufficient noise such that you kind of exceed some or fall below some SNR threshold to where like the signal is a lot of noise, you can sort of trick the system into, or like you're kind of obscuring the actual underlying information about the instrumental, and past some critical threshold, the model will actually, try to learn the task of generating an appropriate instrumental as opposed to learning the task of reconstructing the instrumental from the artifacts.
All right, let's thank Chris again. And I really want to thank all of the speakers and participants. This has been a fantastic
And the
scene.
organizers, thank you so much.
Thank you very much.